work that is before them. Our job is to ensure that there's coordination amongst the agencies, that there's compliance with the laws, and to provide oversight, as well as disseminating information. We are headquartered in DC, and we opened our Alaska field office last month. I was here and introduced Krista to you at one of last month's meeting, and she's here with us today. Coordination amongst all the federal agencies, as well as the state agencies, is critical to the success and to the expeditious construction of this pipeline. We are the lead on development of project implementation plans that will facilitate the roles of the federal agencies participating in the pipeline effort. We are working to make sure that those implementation plans lay out in timelines the work that each of the 22 federal agencies that have a role or a responsibility will do, and how those agencies will interact, and also attempt up front to deal with any disagreements over roles and responsibilities between the federal agencies, so that we don't have those fights when we actually get into the NEPA process. We've also begun negotiations with the state of Alaska on a joint monitoring and surveillance agreement as called for in the statute that will help oversee the final design and construction of the project when we get to that those phases after the EIS is complete. But expedience is crucial at every step and every phase of the project. Delays and unwarranted stipulations will add costs. They'll add costs to the project, costs to the tariff, and could very easily result in the whole project becoming uneconomic. We will conduct compliance and oversight reviews of the agency's work to ensure that no federal agency attaches any term or condition not required by law that could impair or prevent progress of the project. We are mindful, of course, that our responsibility is to ensure that the pipeline is constructed in an environmentally responsible manner, so there clearly have to be balances. So what are the major challenges to getting this pipeline built? You've heard from the proponents. For the purposes of this talk, though, I've identified 4 categories. They're the ones that we're trying to address at the OFC, or at least get in front of one by one. But there are linkages, of course. The most straightforward, but not necessarily simple of the issues, are the technical ones. They're solvable. They'll require world-class technical expertise. There are also economic issues. The project will utilize approximately 2.5 million tons of steel, and a 2004 estimate had the project creating 54 million man-hours of work. 54 million man-hours of work. At the same time, the $26+ billion cost of the project will need to be financeable by the middle of the next decade, and the tariffs that I talked about have to be low enough to attract shippers, so that the delivered cost in the lower 48 can compete with other gas supplies in the lower 48. But probably the most interesting, and by that I mean challenging issues, are the political and the process issues that surround the project. I want to talk, though, about the technical challenges. They are straightforward, as I said. They're relatively easy to address if we have good science. Construction in permafrost. Much of the land along the pipeline route in Alaska is permafrost. It's continuous in the north, discontinuous in the middle sections, and leads to areas near the 60th parallel that are subjected only to seasonal freezing. But even that freezing and thawing in those areas can cause the land to shift dramatically, placing major stresses on a buried and chilled pipe. The geologic instability of routes through permafrost put challenging demands on those who design and construct pipelines in cold regions. We have to get it right the first time. We cannot make any mistakes with the design of this pipeline. You're Alaskans. I don't have to tell you, as I tell people in the lower 48, that the second major technical issue involves the difficulty of construction in the Arctic. It is difficult to protect a labor force when it's 60 below zero, or when they're working in very remote locations. And machinery tends to have a mind of its own, and it is, of course, demonic. This will be the largest high-pressure gas pipeline ever built in the Arctic. At this time, expected design will use 48-inch pipe, X80 steel, and 2,500 to 2,600 psi. Pipeline Hazardous Materials and Safety Administration, better known as PHMSA, and the Canadian National Energy Board will harmonize requirements on both sides of the border to withstand the extreme Arctic conditions. They've already begun that work by doing a study to look at requirements and standards on both sides of the border. The Canadians do have some different standards. This is not rocket science, and it's also not new. Obviously, pipelines that cross the lower 48 Canadian border have managed to meet at the border and somehow mesh up and work. So the NEB will work with PHMSA and with the state to ensure that the standards are harmonized on our portion and our border of the pipeline too. The last thing we want is for frost heave to damage the natural gas pipeline. PHMSA is an agency that perhaps isn't that well known in Alaska, but they're well aware of the presence of the permafrost and the issues and the challenges that that will present to the design team. They recognize the continuous or periodic monitoring may be required to confirm compliance with the design. The technical design basis review by PHMSA will be used to ensure that the pipeline owner and operators are considering all of the criteria in the safety design, construction, and in the future in the ongoing operation of the pipeline. And PHMSA is actually staffing up here in Alaska to have more people to work on this project. Now, part of the reason that the challenges of the design are so important is because the climate in the Arctic is changing. And it's important that we understand that the permafrost changes and the other effects that climate change may have on the pipeline after its construction. Permafrost trends, of course, need to be incorporated in the design so that this pipeline will last from 30 to 50 years. We assume that areas of solid permafrost will be displaced by discontinuous permafrost as the change progresses. The University of Alaska is already working with the State of Alaska Geophysical Surveys and the U.S. Geological Survey. I can shout.
Where's the other microphone at?
Girl's getting it.
Oh, we're wasting minutes for that tip-off.
And your favorite team is?
Memphis.
Sorry, Drew.
It will be the final.
There aren't any cheers. Thanks. Okay. So I'll give them all a plug again. The University of Alaska is already working with the State's Geophysical Surveys and the U.S. Geological Survey. They've been working together to both map and model the changes that we've seen already and what we may see in the future. On the screen is a model that demonstrates the range of permafrost in Alaska from 1950 to today and how it is forecast to shift by 2100. Now, of course, your RDC crack staff always has all of these slides up by an hour after we do these presentations, so you'll be able to go back to your offices, pull it up, and look at it more slowly. But the areas in red are permafrost free. As you look further north, the colors shift to light blue and then dark blue. The darker the blue, the colder the ground temperature. Watch what is forecast to happen. Remember, this starts in 1950, so some of what we've already seen goes through to 2100. It's pretty stark, isn't it? Okay, I'm going to play this map one more time, showing you from 2000 to 2050. This time we're going to look at the forecast change every 5 years. Go back. I think it's important that we all see this.
Last 9 years.
So obviously the challenges that I'm talking about trying to design for permafrost today, discontinuous permafrost tomorrow, is a huge challenge for all of the engineers and geologists who are working on the line. And then, of course, there's the seismic activity. Alaska records 52